So what are we gonna do today? We're moving on with the D-Wave quantum portfolio optimization stuff. Is everything here plugged? Yeah, I think it's everything plugged. What we want to do is I want to go in Anaconda PowerShell prompt, and we should open the Jupyter Notebook. So this is in basically CD workspace, and what do we have here? So we have the portfolio stuff, Jupyter Notebook, that should fire it up. And let's go get the paper again. Cool. Yeah, I don't know how many times I've downloaded it, that's the problem. So I can't remember whether I have these things or not. Here we go. So we have the notebook is now here. Maybe I should do a screen split. Cool. Or yeah, I'm not sure if that's going to be useful. Okay, but should maybe, can I zoom these out a little bit? Okay, that makes sense. That looks better. And here we are at the, so where was I? I was at the, I think at the last, I did think points 1 to 3, and now what we wanted to do is we wanted to go ahead and actually compute the CQR. I think that was the next step. Is that correct? Is that correct? Exactly here. The summary values, the Sharpe deviation, the Chicago net score for an all asset portfolio. Okay, yeah, so that's for one portfolio. So what do we have here? So so did I finish the covariance? So we import the stuff. Let me just go through this again. Then we have like these asset data that we downloaded from Yahoo Finance. And so this is loading the data. Then we kind of have the asset matrix here. Market summary is there. So I was getting the whole thing into a matrix. Then I was calculating the market summary. And I think that was basically, it's just a big array. So it's the mean of all the assets. Again, I don't know if these are the right things to do and the right way to calculate them, but I just want to get some numbers, okay, and then we'll figure out whether we need to change these, so we can change it easily. The covariance. So for the covariance, we're iterating over the asset keys, and we're doing covariance between the asset and the market. Okay, and then we're doing calculating the beta, which is the covariance divided by the variance of the market summary. Okay, and then the asset covariance, so the covariance between each asset, each pair of assets. Okay. So you have like between AA and AAPL, and this is it's a matrix actually. So that's why I think there's a bit of redundancy here, because AAPL underscore A should be the same. Let's check this out. So what if I print, how is this called? Asset cov. So print asset covariance of these, and print asset covariance of these. It's kind of the same, but it's transposed, isn't it? Or is inverted or whatever. These terms are the same, and those are, yeah. Yeah, exactly. So, but whatever. I don't know if there's a better way to store these though. Should probably store this in a matrix actually. Well, actually I should be storing these. I should probably just do one pass. That's probably a better way to do it. Like AA with the rest, and then I should probably just do a pass. Not like, you know, not not just like a double for loop. But okay, we can correct. I don't know how it's gonna. How do we have to then later use these? We'll see. We'll adapt this. Okay. So what we're gonna do now is we're gonna calculate the summary values for an all asset portfolio, the Sharpe ratio and the Chicago net score. How do we do these? How do we do these? Sharpe ratio. What is the Sharpe ratio? So it's here. So so it's there's also the matrix form. I don't know what it is that we want. Do we want the, so this is whatever the W is. The work is structured as follows. I keep like not knowing what this E is, but maybe I should just search for these somewhere else. Definition. Accept. Accept this thing, come on. Now. Return to the portfolio minus the risk-free rate and the standard deviation of the portfolio's excess return. The risk-free rate could be a US Treasury rate or yield, such as the 1-year or 2-year Treasury yield. Divide the result by the standard deviation of the portfolio's excess return. The standard deviation helps to show how much the portfolio's return deviates from the expected return. Okay, so this, what? So we have the beta is the ratio of covariance of a portfolio with the market over the variance of the entire market. So we've calculated beta. We have it, right? We have asset beta. So RA is the return of the collection of assets. Return of the, like, the thing is, I'm not so sure. So what the, I'm not so sure if return is the price. Like, so far I've been using the price, I think. I've been calculating these based on the price. If I open these file, if I open one of these files, like if I go here, open the Explorer. Oh, sorry, it opens in a secondary screen. That's all fine. Workspace. And I go to portfolio optimization and beta. And I check like one of the CSV files. Because that's probably the wrong thing to do. So No, I think I took the price on close. 1, 2, 3, 4, 5. 5. I'm using 4. I don't know which I'm using. But like, what I want to make sure that I'm calculating this with the right thing. So with the right, that I'm calculating the right thing, like the variances and the covariances, because I'm using the price. I think it's in what I should use the return. I mean, it just says covariance of each asset. So how do I calculate the return? It's the return of a collection of assets. Calculate return of assets. Dividing your business return on assets is not like of investment stock market. How do you calculate return on investment for stocks? Subtracting the initial value of the investment from the final value of the investment, which equals the net return. Then dividing this new number, the net return, by the cost of the investment, and finally multiplying it by 100. Makes sense. But like, how much money? It's the return of the collection of assets. For what? Like for the 1 year period? I guess so. It's the return of the collection of assets. It's the risk-free return. RB is a risk-free return. And W is a vector of weights for assets in our portfolio. Okay, so in this case, ratio of currents of portfolio with the market over the but I don't know what the E is. That is bit confusing. And why you're adding the risk-free return again. And the denominator is the standard deviation of the collection of assets. In matrix form as these. From here we develop the Chicago quantum ratio. Okay, so I need to calculate the standard. I need to calculate the standard deviation for sure of the portfolio of like picking everything, right? Like so I guess what the portfolio would look like is probably something like these, right? Where I say, well, so I'll call this all asset portfolio. And this is basically like, you know, just saying like we're gonna peak all of them, okay? So this for sure. And okay, so and what we want to do is or maybe I should just it should just be an array, and I think we should consider these being like the order, whatever. But how do I calculate then the standard deviation of what? Oh man, I'm so lost. What is this E, man? So W is this is W, right? We'll just call it W for now. So this is W. Then we have beta. We'll call W all assets. We have assets beta. So I guess I should just then, yeah, that's just multiplying these and these E. I don't know, and then the return is the return on the collection of assets. How do I return? So do I just take like the last value, the last price of each asset, and kind of minus the and minus it with the first one, and then I just take that like as my return. It's a really naive asset return. I'll just do it this way, and then we can yeah, I don't know. So I'll just do it like this for now, because I don't know, like you should have to put in there how much you want to invest, I guess, and like okay, so the asset return is like this, and then what we want to do is we want to kind of so for asset key in asset return, right, do the following. So we want to have the last so is it asset data, or what do we call it? Asset data, exactly. We want to get asset data first and last, so we want to do something like asset return for asset key equals basically asset data asset key, and sort of the last one, like how do I get the last element of an array? I guess it's something I can index it with -1. Python get last element of array. Yeah, -1, and we minus with a 0 element. It's a really naive way to do this, but like, yeah, that's kind of my return, right? Like, is the price going to be higher or lower? Let's just like do it like this. That's all fine. And now we'll print this guy. Print as return. Okay, cool. So we have here. Yay, perfect. Some negative values. We see some positive values. Now this is the asset return. So we have the asset return. Now, how do we calculate the and I guess the portfolio return is taking each of these. It's like if it's 1, then add it up. If not, like yeah, cool. So and the RB is the risk-free return. Investopedia risk-free return. This is something to do with like something that's like A theoretical return attributed to an investment that provides a guaranteed return with zero risk. The risk-free rate of return represents the interest on an investor's money that will be expected from an absolutely risk-free investment over a specific period of time. The yield on Treasury securities is considered a good example of risk-free return. U.S. Treasuries are considered to have minimal risk since the government cannot default on its debt. If cash flow is low, the government... Okay, get it. How do I calculate that? The capital asset pricing model, one of the foundational models in finance, is used to calculate the expected return on investable asset by equating the return on a security to the sum of the risk-free return and risk premium, which is based on the beta of a security. The Kaplan formula shown these. Yeah, but I wanna. How do I calculate these? Risk-free rate. The beta of a security. The return on a security. So what is the risk-free rate? The beta of an asset times RM. We don't know what RM is. Rate of return. I don't know how to calculate that. The yield on the US Treasury securities, that's what's used. And thus, investors commonly use the interest rate on a 3-month US Treasury bill as a proxy for the short-term risk-free rate. Just give me an example. I don't know. I can probably just move on with 0. Risk-free. Risk-free rate. So 10-year Treasury constant maturity. So the price of non-securities corporate bonds. Treasury securities are considered risk-free since are backed by the US governments. Whatever, we'll just pick, like, I don't know, 2.63. I guess that's what we'll do. So the risk-free return. So we'll call it, like, yeah, risk-free return 2.63. Whatever. Good. So we've got that, and Okay, and now the standard deviation. So what's a collection of assets? Standard deviation. NumPy standard deviation. NumPy standard deviation. STD. What do we give it? Specified axis. So, but it's the standard deviation of collection of assets. I guess each asset has a standard deviation, right? In matrix form. So is it just the yes a bit better? Yeah, I guess that's what we. It's maybe the average standard deviation. I don't know of the collection of assets. Because I guess each one has. So I would just kind of copy that and go ahead and do like STD and then asset STD STD. What? No. Exactly. Of asset data as a key. That's probably what you want to do. Print asset STD. So we want to start deviation none. What have we done? Asset key and asset beta. Sorry. Sorry, I just probably killed asset beta. That's what happens when you copy paste code, There you go. So we've got the standard deviations. And then standard deviation and standard deviation of a set of assets, of a set of stocks. Like, is it just the I guess I could just do the STD of these, right? So then measure for amount of variation. Of the portfolio. By squaring the weight of the first asset and multiplying it by the variance of the square of the weight of the second asset multiplied by the variance of the second asset. How much the investment returns deviate from the mean? Okay, so actually it's not just so it's got to do then with the okay, it's the square root of, and then you're squaring the weights of each asset and times their standard deviation. Okay, cool. But so on each return of the collection of assets. So this is the vector with the weights. This is the beta of each. Yeah, also a vector of the weights of the betas. And then we are like I don't get like, is it a number or what is these? Or is it like Sharpie ratio? You know what I mean? Like W is a vector of weights. Standard deviation of the collection of assets. Then we develop. Okay, I don't get. I'm I feel so stuck. It's half an hour ago. It's half an hour. It's gone like through just like these, man. It's a weight. It's a vector with weights, and then it's times these, and then these are just like their return in the collection of assets. So these are just single values, right? Like it's the overall return. What this says is return of the portfolio. It should be a number minus risk-free divided by standard deviation. So I'll just do I'll just do this. So the Sharpie ratio in this case is basically the. So I need to calculate the. So I have the risk-free return. I have the asset return in here, but what I need to do is I need to add all the things up. So total return. I guess what I would have to do is I would have to. I'm gonna just add them all, right? Like, but I would need them and I would need to actually have probably build a function where, you know, given, given an actual vector of weights, then I can it can calculate what the return of the portfolio is, because then it's proportional to the weights in there, right? So all asset return. And then basically I don't know if there's a faster way to do it, but like I'll just go ahead and do it just like these. As a return. Because we know it's all with equal weights, as a key. So we also have these here. Okay. The portfolio return. Yeah, I don't know if I'm doing this correctly. Oh, but this is the rate actually, the risk-free rate. Yeah, that is probably not. And so the standard deviation and the standard the standard deviation of the whole thing was the basically risk-free return. I'm lost. All asset return, all asset STD. So STD non, and then I'll just kind of copy paste these and basically say, you know, so what we're gonna do is that so I'm just gonna add everything, right? and then at the end we'll just square it because it's like equal weights is 1 like so this basically is just 1. So what I would just do is I would add all these things up because I shouldn't care about the squared ones, and so asset STD as a key. So we'll just add things up, and then at the end say that this is basically square root of like this is the way that you run it. I think so. And we'll print these. Sorry, it should start with a 0. Okay, so now we basically have that the Sharpie ratio, all assets is basically the all assets return minus the risk-free return divided by all assets STD. And so if I want to go ahead and print that, okay, that's what we have. Now again, I'll probably need to plug in a couple of functions in here to calculate these for a given portfolio, but we'll do this later. I don't know. I really don't know what the minus RB here is, the plus RB here is. I don't know what the E here is, but I know what this is here. It's this risk-free rate, whatever that is. I just use 2.70 something. Yeah, but we understand what the ratio means, right? So this means it's the return that you would make just purely because of the risk you're having, and then you divide it by the standard deviation, so you're accounting for how much volatility there is in there. I mean, there's just a big storm going on outside right now, but it's cool. Okay, what's the Chicago quantum ratio then? Is the covariance where covariance IM is the covariance of the ith asset against the entire market. So it's not using the risk-free stuff. It's what are nominal assets? I think I searched for these already, but like bond or share stock. No, they're not real assets. If you're confused, yeah, I guess that's what it means. Yeah, okay. Risk-free investments have a near zero covariance with the entire market. Okay, but again, like, I guess what they mean is that you take the covariance of each asset, the standard deviation of each asset, and you're multiplying these for, so you get a CQR for each asset. In matrix form. We explore these formulations by a variety of classical methods, which one will find in 3. Both formulations are outrageous, and thus neither is properly suitable for a quantum annealing solution. Rectify this by exploring the natural logarithm. Okay, let's get the CQR though. It's the covariance of each. Where did we have the covariances? Asset covariance. But it's of each asset with the market. So, didn't I have these though? Wasn't this better? No. It was market covariance. Okay, we got it. So it's here. Oh, but it's an array. Yeah, but I think I can take the value like. Yeah. I think I could. I think I could just take one of these values actually. I think I could just do these and then do the 0, 1, I think it was. That equals these. I think that's it. So we just get numbers exactly. And so, but like again, what do I take? Do I just take like the average CQR? Like I don't know what it's not clear what they're using here, right? It's not clear what they're using to then calculate that over the actual portfolio. This is not improvement of the Sharpe ratio in terms of computation, as we need not consider nominal assets. Risk rate. Okay, we understand this, but now, so now we're exploring the natural logarithm of the Sharpe ratio. It's like, how can I know these? Like, how can I know what these is? Maybe I should just take a screenshot and and ask the Chicago guys. How do I do this? Yeah. Oh, sorry. Here we go. So I'll just screenshot these. So slow. Tweeter. What is these E? I just need to know these E, man. Why is it going so slow? Tweeter. So, no, what is this? Chicago. Why is it so slow? So, capital. In the attached equation. Is it the average or what is it like? Math notation. Capital E. Means to raise the number that comes. Where it means to raise the number that comes after it to a power of 10. No, that's not. List of mathematical symbols. That's not what I meant. Like, yeah, we're not gonna get anywhere here. It's like there should be. No, I'm not going to search for capital E because it's going to be everywhere. But that's just going to be impossible to find, I guess. Okay, whatever. But so the natural logarithm of the risk-free return minus the natural logarithm of the standard deviation. Why is that better? In formulating a consistent quadratic form. Finally, we settle on the Chicago net score, which is given by RW. R sub W is a weighted portfolio, and alpha is a real number. In most experiments, we choose an equal weighting, where n is the number of assets included, and we choose alpha neo 1. These are not requirements, but they do make the computations in D-Wave slightly easier. There is a wide open question as to finding optimal weighting and optimal alpha. We explain how to formulate the quadratic form for use on a D-Wave in the appendix number 4. So here's this E again. Okay, so it feels like that was a bit useless, everything. But like, number 4, so how do I get there? In the appendix, I guess. Or is it, no, it's here, it's not, it's chapter 4. So, okay, so how do we do this? So how do we cubo this thing? The main thrust of the decision is to formulate the cubo, which then presented to D-Wave produce similar results to the classical Sharpe ratio. Consider the following. The Sharpe ratio is defined above as these. The numerator can be expressed as a simple dot product, where mu and W are the expected return and the relative weight of the ith asset respectively. Okay, so the sum of expected return, yeah, I mean, I feel I've been losing, I feel I've been wasting the last hour or so. So the sum of the expected return times, you know, each relative weight. The denominator can be expressed as the square root of a quadratic form. So okay, so the standard deviation is what they express as the square root of these. So what's the formula of the standard deviation, by the way? Formula. Okay, so it's the square root of each value of the population minus the mean squared divided by the size of the population. Okay. And here they're saying that this can be expressed as, so we've got like the square root, right? And then a quadratic form where basically what they do is the sum of the, so where is V? V is the variance. So the variance of each asset, and Qi is basically, it's qubit, right? So qubit 1 represents asset 1, and so we've got the variance. Oh no, where Qi, it's a binary classifying whether the ith asset is in the portfolio or not. Okay, and 1 will immediately recognize this as deviation as in the initial formula. 1 will also recognize that the Sharpe ratio is not a proper quadratic form and is not suitable for D-Wave. times the covariance between each asset. Oh, it's like, why all this stuff? We find the Chicago quantum score solves this problem and can be presented as a quadratic form. Okay, but like, you don't give the actual solution here in terms of, this is just a Sharpe ratio. But the secant is variance, and like, how is that like? Okay, so maybe this. So this is the variance. I get it. So this is kind of the first part of the quadratic form, and then I don't know what is it. Is this E the expected return? I don't know, what is it. Developing the cubo to number of assets in a portfolio. A universe. You consider a universe U of n assets. When dealing with a single asset portfolio, we only consider linear terms, in particular when we have a lower triangular matrix or a zero diagonal matrix. Products of the form, blah blah blah. What is this? This would pick off only the linear terms. In this case, we concisely model the inverse Sharpe ratio on qubits and use a penalty on the couplers. D-Wave finds one asset portfolios with the highest ratios. Okay, so you just add penalties to the couplers so they are not picked up, and we pick off only the linear terms, the variance based on this formula, or what? We create a unique cubo for each size portfolio by applying the weights directly to the matrix. Moving to two more assets, we have substantially more work to do. So looking at a single asset, there are no covariance terms to deal with, and we can embed the inverse Sharpe ratio directly, the inverse Sharpe ratio directly onto the qubits. We create a unique. Like, it's so confusing because they keep switching from Sharpe ratio to the CQNS, and I have absolutely no damn idea what they're doing, what they're explaining. They want to do the inverse of these, I guess, so then you have the quadratic part like as a multiplying factor, and then all these other stuffs just as a constant that you can we can embed the inverse Sharpe ratio directly into the qubits. We create a unique cubo for each size portfolio evaluated by applying the weights directly to the matrix. So Qi and Qj can remain binary. We divide the linear terms by n and apply the linear affine transformation. We divide the variance terms, the diagonal entries, by n squared times n minus 1 to avoid duplication. I guess they're talking about a cubo matrix, right? The cubo matrix. And reverse the sign on the linear terms. Finally, we apply a scale factor to the cubo and write it into our n times n matrix for processing by D-Wave. Like an example would help, actually. You have facets on which to choose. We define the shift factor to the way for each desired size portfolio. We add a penalty for exploit portfolios with different sizes while maintaining accurate values for desired portfolio size. So it seems the way that you're fooling the D wave to pick like other sizes are by adding the penalties. But still, one thing that it's not really clear to me is the metrics form they talk about for the cubo. So D wave cubo metrics. I guess that's. I don't know if I checked that last time. I think I checked that last time. Yeah, I checked that last time. Yeah, okay. Those are the single terms, right? And then the upper terms are like for the couplers 0, 1, 0, 2, and 1, 1. By y like an n times n matrix. So if I'm getting it correctly, what they do is they just develop a cubo that is just a variance with the market. Maybe let's give it. I want to try this. Okay, I just want to do something just for like the video. So maybe I'll just take that, make a matrix out of these. Okay, so or let's launch D-Wave, the D-Wave thingy here. I want to do the ID workspaces. Yeah. So let's work with this email. Should work with this email. And here I think I had a workspace on. Simulation programs. D-Wave examples. Oh, wait a second. I had like a IDE. Did I create a repository actually? Did I do this? Let me just log in. So you, just in case. I just want to log in and find. Oh, come on. Sorry. Two-factor authentication. It's good actually. Stay safe. So. Oh, I don't have these here right now. Oh crap. Whatever. I can't actually open this up right now because I have the wrong phone with me. So we'll just, you know what? We'll just use some of these examples. Good. And I just wanted to get the so the sum of the covariances divided by these. No, but that's not the point. The point is to have what is the point actually? So still loading. What I want to have is I have the market covariances, so I have this here. So if I now market covariances, okay, so if I now do these, right, and I just what I do is I sum these things up. No, I'm not going to sum these things up. I'm just going to make a matrix out of these, right? NumPy create diagonal matrix. I think you can. I think there's a shortcut for these, right? Is this the way it's supposed to work? Diag and then the array. NP diag, then the actual market cove. Oh, sorry, it's a Python turn dict into array. Can I just query the values? Items. Sometimes these list state values. Okay. So list. There we go. Yeah, there we go. Okay, so here we have the diagonal matrix. So this would be basically the cubo, right? Test cubo. But then, oh, you wanted to add a penalty actually. So how do I do that then? Is there a quick way to do these? Or we'll just do it the funky way. So test cubo, and basically we'll just print test cubo. So I'm going to print this now, and then basically what we should do actually is oh, come on. What is the CPU? 56%. So NumPy iterate or iterate over all elements of matrix. Can I just not modify like modify matrix elements that fulfill the condition? Can I do this? If condition is met, yeah. Aha, I can do these. Oh, that's nice. Okay. So I can say test cubo. How? Test cubo bigger than 0 or equal than 0. Then say, I don't know, like 100. Okay, yeah, that worked out. Nice. But we should probably negate the... Should we negate the actual diagonal map? Because I think they do these, right? No, they divide the linear terms. What do they do? So pick the linear terms. In this case, we consistently model the inverse Sharpie ratio and qubits and use the penalty and the complex difference. Single asset portfolio, we only consider the linear terms in a cubo. Moving to 2 or more assets, we create a unique cubo for each size portfolio by applying the weights directly to the matrix. So Qi and Qj can remain binary. I don't understand that. We divide the linear terms by n. And apply the linear affine transformation. Do I have to divide the linear terms by 10? So how many portfolios we have? 1, 2, 3, 4, 5, 6. So I would say if cubo is different than 0, then, or we can just as well like do that. Okay, equals 0, 100. So that divides. Oh, I cannot, like, how can I cannot do that, I guess. Can I just divide the whole thing? I think I can probably divide the whole thing. Yeah, can divide the whole thing, okay. Because if the rest are zeros, I don't care. And I should probably multiply it by -1 maybe, just to make sure that those are negative, and so they are lower values. I have no idea. Yeah. And so I should probably then take these matrix and drop it in here. So BQM conversion offset general program BQM basic programs Cubo. So here or just give it like this. I just like, why not? Why not just like, you know, I have 6, come on, like I have 6 assets. I guess I can. Oh yeah, but then we'd have to add all the quadratic terms, blah blah blah. Python is not installed. But that's like, whatever. How do I do these? So how do I do these now? I've basically literally the matrix in here, and I just want to what I want to do is I want to embed it, I guess. So D-wave embed a cubo matrix. I guess it might be easier to just install the SDK, isn't it? Like, can I just resources? How can I just download that? Like, oh, come on, access code in my email. Are you kidding me? Let me check. I ain't got any email, I think. I ain't got any email. Resend the code. There you go. So the code is 410, 153. So I want to download the thing. I just want to download whatever SDK, Ocean Software. Documentation, tools, here. I don't have your GitHub. Ocean SDK. Okay, so here we go. So we have these. How do I? Okay, I should just basically just use that probably. Okay, so I'll open a terminal. So basically, Anaconda. Come on. Come on. Peep. What? What happened? I hate when this starts lagging so much. Come on. I want pip install Deviation SDK. How do I? Okay, so pip install Dwave Ocean SDK. Hopefully this will be compatible. And how do I then use that, right? Software subdivision, software stack. learn more. Client get solver. Okay. Is minimal implementation of REST interfaces to communicate with the D-Wave sampler. Cloud client. So you get a solver like these. Okay. It's still installing. I don't know how long it's gonna take. But we can try this quick example. But like from config as client. Like how does this thing know my actual API? Setup. Install, blah, 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 Pro Inspector, configuration file. Oh, this is where you have probably the API endpoint, authentication token, all that stuff. I don't know if I'm gonna make it now, it's just too complicated. Oh, not complicated, but like... Yeah, that's not easy to find. So I'm downloading these and then... So that's the installer. What's these? Try model, class contains sizing, try consumer models. Introduction. Die mode. Examples, blah, 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 blah. Okay, so this is about, like, this is how you're just library to create the models. Getting started. That's probably where I should go. Initial setup. Installing Ocean tools, configuring access to D-Wave solvers. This is where I should probably open up both. This. Did this get installed? No. Who cares about Circ though? Okay. Windows. Install virtual environment. Blah blah blah. Ocean software. Alternatively, then set up the environment. Install configure Ocean tools. This is before you start writing code, you complete the setup of the environment with two last steps. Adds non-open source tools such as Pro Inspector, configure access to D-Wave solvers. Okay, it includes an interactive client that sets you through the setup. That steps you through the setup. The interactive setup and commands setup. Not open source contribution tools. If you did not install contributor package with setup command. Okay, so basically just gotta go through the install part. Just like that. Yeah, I guess we're not doing it today. I'll just drop it here. It's been like an hour and a half almost now. But basically what I want to do next step is just I just want to send these and see what we get out of it. But this whole thing, it's just I don't know. I think I got a reply on the tweet. Hey CJ, cool. This helps. I think it's expected value of a random variable. So basically the average, right? Euclidean space, definitely not. The expected value of a random variable or a field in a tower of fields. This is from Wikipedia. It's probably expected value, as I said. Okay, so this means that where's the paper stuff? I don't know already where these ones. Okay, so this means is the expectation value. That's because it's a single ratio. But then, like if we work with actual matrices, then that doesn't matter. It disappears. So we probably should work with the matrix version of it, of the ratios, which is then just the actual ratio per, associated to each asset, like these, right? Like, so there's no E anywhere. It's just a covariance. Okay. This transposed and expected value of the variance at is expected value of the weighted portfolio. What? Wow. I don't know. It's really obscure to me right now. What these really. The variance. Is var variance? Like, I don't know. They don't explain that either. Um, at the end of the day, it just seems like what they do is they just put the variance in the linear terms and the covariance in the nonlinear in the couplers. What's more like 2 times the variance? It's really, I don't know. They could just start it like they could just have started this way, I guess. It's a lot of stuff just for something that seems a bit then. I don't know. I have mixed feelings. I have a big mixture of feelings right now. So this is done, and we'll go through the setup in the next video. We could also use QCware though, but let's run this locally because I have the data locally. So what we'll have to do next time is just run the where was that? Just the SD-Wave setup, because now I don't wanna. It's gonna take a while to install all the stuff, I guess, and then yeah, and I think what I'm gonna try to do is I'm gonna try to get the one asset portfolio example done. I'm gonna try to do a 2 asset portfolio example done, and I'm just gonna call it a day. Just gonna call it a project, I guess. It's yeah, awesome. I don't know. It didn't feel like really productive today.